So don't worry, I do have built into the schedule plenty of time for doing much more workshop sessions with the exercises, because I think that's really, rather than just seeing a load of material and theory presented, I think it's really important that we get a lot of practice in problem solving through the various exercises. And the teaching schedule that's up on Moodle, there's even a bit of pairing I might do to that, to take out one or two things in order to allow us kind of more time, because there's a couple of technical or a couple of substantial topics to come, allow us to give more time to that and to free up more time even for just doing loads of work with the exercises, because there's hundreds of exercises in here. They're all really good, and that's the important stuff as well. Okay, so a quick recap on where we were. So you'll remember in proving Lagrange's theorem. Proving Lagrange's theorem, we had a group H, group G, subgroup H, which at least contains the identity element and probably some other elements in there. And in the course of proving Lagrange's theorem, remember Lagrange's theorem applied to a finite group. So when the group G was finite, so it might have a lot of elements, but there's just a finite number of them. So just drawing a Venn diagram for the second picture of the knot of the group. So Lagrange's theorem said the size of this subgroup H is a factor of the size of G, okay? Which is really nice result to know. It's really kind of pleasing, kind of the way these things fit together nicely. And the way Lagrange's theorem was proved was that we were able to, starting with the subgroup H itself, we were able to build a partition of all of the elements of G into different subsets, which we called cosets. We called them left cosets. So we had a G1H here, G2H, G3H, and so on. So this was the partition of the group G into the various left cosets of the group H. This representation of, say, this left coset is G1 times H. That's not unique. You could choose any of these other elements in here. Let's say this element was a G1 prime. This is also equal to G1 prime H. Okay? So all of these elements within this coset are all equivalent to one another under this, meaning that they both represent the same left coset of H and G. Okay, so this is how we split G up. And then what did we prove? Well, we proved it was a partition, so we proved none of these different sets overlap in any way. So whenever you hit G on the left with the group element, little g, whenever you hit it on the left with two different elements, either they're two completely different sets or they're the same set. It does never have partial overlap. Okay, so you do get a partition. Everything's accounted for because every element, little G1 prime, say, is in the coset little G1 prime times H because the identity is in H. So one of the elements in here is just this element times the identity, so in other words, this element itself. Then the crucial part for getting the divisibility result was proving that, in fact, all these subsets, they all have the same size. They all contain the same number of elements. Yeah. And that was basically down to the cancellation law in group theory. That when you multiply everything in H on the left by an element G, you get a new bunch of elements, perhaps, but it's injective, one-to-one correspondence. You can never multiply two different things in H by the same G on the left and have the products be equal, because then the two things you multiplied would have to be equal as well. Okay. So that was how we proved Lagrange's theorem. Now this partitioning of the group G is interesting. It shows you how, for given a particular subgroup, you split the elements of the group up in a certain way. But now we made a conscious choice, arbitrary choice, to deal with left cosets. You can play the whole game in the same way, but by putting the elements little g on the right, okay? So we can also play this game, let's say, run this whole argument, set up this whole system, play this game with right cosets. And in general, that would give you a different partition of the group G, even though you've started off with the same subgroup H. Okay? But then this leads us to an interesting special situation. Okay? And this is where, okay, so I'm just giving a recap of the last lecture. I'm not going to give the whole thing again. The interesting special situation is when the two partitions are actually the same. Okay? So these two partitions, which in general might be different, because there's no reason beforehand to expect that left cosets will always be the same as right cosets. But when these two partitions are the same, i.e., a special type of subgroup. Now I'm going to switch to the letter N now, because the term for these is normal subgroups. So it's a special type of subgroup N satisfying. And the thing it satisfies is this. Okay. For every element G from the group G, the left coset is the same as the right coset. Okay. Yeah. So that's special nice behavior. It means that from what we saw before, this different way of analyzing it, with left cosets or right cosets, and the picture looks different. Well, in this special case, for these special types of subgroups, it's going to look the same. Now, it's important to note that we're not saying here, we're not saying for all G and for all little n in N, G times little n is equal to little n times G. We're not saying that. Okay, that would be an even stronger result. I would say that every element in the subgroup N commutes with every element from the group. Okay, that's a lot stronger. Certainly that would be true in abelian groups which everything commutes with everything else. In those groups, every subgroup is normal. So when you're in an abelian group and you look at left and right cosets, it's the same thing, because it doesn't matter which order you multiply things. It's always the same. So a normal subgroup is not when everything commutes on the element level like this, but where, as a whole set, the left coset contains exactly the same elements as the right coset. Okay, but the individual, the G times any particular little n will probably be different from that little n, that same little n times G on the right. But the G times a particular little n, if it's normal, will be equal to another of the elements from the subgroup N times G on the right. Okay, so it's on the level of the coset that you have in quality. Okay? So that gives us then this nice picture that we have the group G, the subgroup N, which at least contains the identity, and then we have the partition into cosets, but we no longer have to specify, are we talking about left cosets or right cosets, because they're the same thing. Okay. So this will be one coset over here, and you can also, it's also like this over here. Here's another coset, G2N, and it's also G2. So no longer have to specify right or left coset. that's what we spent some time exploring in the last lecture. Note an equivalent condition here. An equivalent condition here is that instead of this G multiplying n on the right, if you kind of multiply both sides, and remember, this, you have to be slightly careful with what you mean here, because here we mean a set of products, G times every little n that here is. Well, and it's equal to sets. Well, if you multiply everything on the right by G inverse, you get this equation, which is again an equation of subsets of G. But it's clear what it means. This consists of every element G times a little n times G inverse on the right. And this is almost an alternative definition of what a normal subgroup is. And it emphasizes the role of this important concept of conjugation. We've seen it come up a few times, and it comes up again and again. It's an interesting construct and kind of a method or an operation in group theory, where you take something and you multiply it on the left and right by an element and its inverse. Okay, G inverse. Yeah, it's almost like, and you'll see this kind of thing emphasized in the coursework. It's quite a natural process. Remember, a lot of the times, the interesting groups you're looking at are groups of functions. Permutations are functions from a set of labels to itself. The dihedral groups, those are groups of functions, symmetries of the plane, transformations of the plane that are symmetries of a particular figure. Another very important example, which we haven't looked at a huge amount, but groups of matrices. Matrix groups are quite important. And matrices should really be thought of as, what do matrices represent? Matrices represent linear transformations. So matrices really are functions from a vector space to a vector space. So if you're thinking of group elements as being functions and the operation as being composition of functions, then the operation of conjugation is kind of like a translation from one scenario to another. So if I have a certain operation, say represented by one of these elements, little n, okay, you can perform the operation n. But then you can think of G as some kind of translation from one description to another. So performing G inverse does the translation one way. Then you perform the operation n. And then you multiply by G, which does the translation back in the opposite direction. So it allows you to view, if the elements are operations, then conjugating by another element is kind of performing the same operation, but in a slightly different setting. Because you translate one way, do the operation, and then you translate back. So, that's very, very vague description, hopefully not confusing, but it just kind of meant to kind of motivate this as an interesting type of construction, conjugation. Okay, so where were we? So it's interesting that when you have this special type of subgroup, and we looked at some examples in the last lecture, you get this unambiguous partition of G. No longer have to distinguish between right and left. And here comes the kind of prize in this chapter. This partition of the group G is actually a group itself under a very natural operation. Okay. So the original group G is the group of these little dots, the little elements. Yeah. They're the elements of the group G, and they're the elements of the subgroup N. But this new group we're going to form, this is the factor group. Factor group of G by N. It's written as this kind of a fraction, G over N, often. Typically not as it tends to be only with the diagonal fraction line, maybe not with the horizontal fraction line. That just seems to be a kind of a subtlety or a convention. Okay, factor group is what Judson calls them, but I think they're more widely called quotient groups. But quotient group is an alternative term. What is this? Well, the original group G is the group consisting of the little dots. Those are the elements. The factor group is the group consisting of the cells in the partition themselves, the subsets, what we should call them the cosets. Okay, so the elements in the factor group are the cosets. Okay, so it's a much rougher view of the group G. We're no longer on the fine level of the detail of the individual original elements of G. Now what we've done is we've clumped groups of them together and regarded them as equivalent. And now the elements of the factor group are just these cosets themselves. There's a much smaller number of elements. If the group is finite, if the group is infinite, then there could be an infinite, well, it could be finite. Okay, we'll forget infinite groups. But if the group is finite, then certainly if you're dealing with a non-trivial subgroup, N, certainly there's a smaller number of cosets than there are elements in the original group. Now we'll specify what the group is now in a second. It's a way of getting a simplified look at the group G. You can extract some information about the original group G from the factor group. The factor group displays some of the aspects of G, but not all of them, because you've lost detail. You've kind of clumped things together. I gave the example yesterday. It's like looking at a country, and on the most detailed level, you're seeing every individual inhabitant of the country. So the 70-odd million people there are in Britain, if we're looking at the map of Britain, you see every individual person. But maybe that's too much detail. So you clump it together, maybe on the level of counties. So you got Devon, all the people in Devon, all the people in Cornwall, all the people in Greater London, all the people in Greater Manchester. So you're grouping the elements into equivalence classes, and then you just view the country as, well, the country is made up of these counties, and the counties interact in a certain way, have a certain relationship. Okay, you're seeing some aspects of the country, not all the aspects, because you're no longer seeing individual persons, but rather on the level of counties. Okay, so it's kind of rough analogy. So this is what our factor. Okay, that's what the factor group is as a set, but what's the operation? Well, the operation is now the operation better not be too complicated. For this to be a reasonable kind of construction, the operation better be natural, and not come via some weird definition. It must be kind of the obvious thing to do. So this is a group under the operation. So what does it mean to perform an operation? Now I'll switch here to the notation that he's using A's and B's. So here's one coset. I'll just represent it as a left coset, but it could be represented as NA because the subgroup is normal. But there's one left coset. I'll put brackets around it because it's a single thing, and there's the other coset. So I have to tell you what the group operation is. What do we get when we multiply these together? Well, if it's going to be a group, the group has to be closed, so it has to be another coset. Okay, so this is a definition. It has to be another coset. Which coset? What is the most obvious coset to associate to this? Yeah. Why would you do anything else? Yeah. It'd be perverse to write it as BA, because that's opposite order to what you've got there. Here you've got the A coset on the left, the B coset on the right. So we should preserve that information and look at AB. And like, the only thing we know about this coset is that it's generated by the element A. The only thing we know about this coset is it's generated by the element B. A and B are the only pieces of data we have. So it's the most obvious and natural way to even begin to set up an operation on the cosets themselves. Okay, I'll even put brackets around the AB just to regard it. This is A times B is another element of the original group G, and it will generate one of the cosets. Okay, so here's your AN over here. Here's your BN over here. You multiply them together under this rule. It takes you to another coset. Okay. So theorem 10.4 proves that this is a group. Now, once we know that the operation is valid and this operation is okay, proving it's a group is just trivial. We're just checking the group axioms and the thing comes through perfectly fine. But I may have pushed that past you a little bit. There's a problem, well, not a problem, but there's an unsettled matter about defining the operation like that, okay? Let's say this is AN over here. So there's the element A. So this whole coset is the coset A times N. Remember, every element belongs to the coset that it generates because the identity is in N, so A times E equals A. So A is in A times N. So here's the coset AN. Let's say the coset BN is over here. Let's say this is the element B. Now, really, when I say multiply this left coset by this right coset, the way I've worked out which other coset it is, let's say A times B happens to be this element over here. So this coset should be labeled ABN. Okay, the way it's worked is I've taken this element A, this element B, I've multiplied them together, and I've gotten AB. Okay. But now, there is nothing special about the status of this A over all these other elements in the coset. And the same for B. There's nothing that picks, okay, I've chosen to name this element B, but it's no more special than any of the other elements in the coset. Right? So what if I chose to represent this coset not by A, but by one of the other elements? So let's call that the, well, I won't call, that's slightly infuriating in the proof there. Okay, so my proof is going to have to stand aside from his proof because the notation is different. So I'm going to say, let's say there's another representative A prime there and another representative B prime here. So what if the cosets are represented differently? So AN is equal to A prime N, because they're in the same coset. BN is equal to B prime N, because they're in the same coset. Okay, so my notation is now departs from the notation E uses in the proof of the book. So the question here is, if I present the product like this, now, according to the rule I've given, this is A prime, B prime, N. Sorry. Yeah? But this is the same left coset as this one. A prime N is the same as A. The B prime N is the same as B. So it's the same product. So these two ought to be the same. There'll be a problem if these two are different. Okay, but I don't immediately know that these two are the same because I've got a different element here. This is the coset corresponding to a different element. Okay. So this is a problem when you base an operation on sets by giving the rule for calculating what the operation is by using elements from the set, using a choice of elements from the set. The problem is I could have chosen a different element from the set, the A prime and the B prime, and instead done the calculation using those. But you see, for this to be a well-defined operation, the thing on the right-hand side here has to be uniquely defined. I can't have it subject to, well, it depends which way you represent this coset and which way you represent that coset. Okay? You can't have that. So these two, in order for this to be a well-defined operation, and this is the problem we're getting at. In order for this operation to qualify for the name operation, in order for this to be a well-defined operation, we need to prove something, a well-defined operation. We need to prove that these two right-hand sides are actually the same. That AB N is equal to A prime, B prime, capital Because without that knowledge, we don't know that this is even a proper definition of a binary operation. But this can be proved. It can be proved all right. And you'll also see in this that we use the fact that the subgroup is normal. So in the proof that this is a well-defined operation, you will spot the point where we use the normality of n. And that shows that you can't set up this system with a non-normal subgroup, with a just ordinary subgroup, which isn't special and normal like this. This game won't work. So you can't form these kinds of factor groups with any old subgroup. It has to be one of these special subgroups which are normal, because it's only when you've got that special property of normality that the operation is well defined. So working with the notation that we set up there, see, if an is equal to a prime n, then there exists a n1 in n such that where do I do this? Yeah, a is equal to a prime n1. Okay, because remember these two are the same on the set level. So a is one of the elements in here, so it must be one of the elements in here. And the only thing I can say about it is, well, it must have the general form of an element in here, which is an a prime times something from the set capital N. Similarly, well, I don't need an F here. I don't need an if there because I know this. Bn is equal to b prime n. That's what I set up there. So that implies that there exists an n2 such that b is equal to b prime n2. And so this is, using this information, we can build our proof. So if we take ab times n there, remember the brackets I'm only putting in for emphasis. The brackets aren't really needed because by associativity, I don't need brackets in the middle of a product. So we'll drop the brackets and we'll work with the idea of general associativity from now on. So this is the set, is this set here, the set of all products a times b times something from n. Remember, we're dealing with sets here. Okay, now I'll substitute. A is a prime n1, b is b prime n2, and this is your set n. Okay. So now this object is a set of elements. It's the set of all products you can form like this, where you take any element from the set n. And somehow I want to work on this and get it to be equal to a prime b prime n. It looks reasonable. There's my a prime, there's my b prime, there's my n, but there are these other specific elements from n in the way. Okay. Now the first thing, now this is run through very quickly in the notes there, but I just want to spell out the justification for each step because it's kind of subtle. The first thing we do is we drop the n2 out of it. Now where's the n2 gone? Well, what justifies this claim is that, I'll put it in red here, since the set n2n, right, which consists of all products, this specific element from the set n, n2, whatever it is, times every other element from n, set of all those elements, that is equal to the set n, right? In the same way, remember when we were forming our cosets originally, we had a subgroup H. If you took any of the elements from H itself, look at the coset generated by that, it's again H. When you multiply any subgroup by an element from the subgroup, it just permutes the elements in the subgroup around. It's still on a set level, it's still the same. So multiplying a subgroup by an element, and that's crucial, by an element from that subgroup, simply permutes the elements of the set. Moves them around amongst each other in a permutation, but on the set level, it's still the same set. So that justifies this equation. Remember, these are equations of sets. Okay, this is good. The n2 has disappeared from the picture. And our b prime is beside n. We want the b prime to be beside n in the final answer. We still got this n1 complicating things. Then we want to do the same thing to the n1. We want to absorb it into the n. We can't do that at the moment because there's a b prime. Yeah. n1 times these elements. These elements here are no longer probably not elements of the normal subgroup n. They would be if b prime is in n, but I've no reason to. In general, b prime could be any element from the group. So I can't absorb the n past that. But what can I do? This is not any old subgroup. This is a normal subgroup. Definition of normal subgroup is left and right cosets of the same. Yeah. And what I was staring at there was the left coset, b prime times. Remember, the whole thing is associative. I can bracket the thing any way I want. So if I consider that as the element, as the set, this is the left coset of b prime. But n is normal, so I can flip the b prime to the other side. Okay, so that's true since n is normal. So that's crucial. If n wasn't normal, this proof wouldn't work. Now remember, I'm not saying that b prime commutes with these individual elements. Okay, if you look at the individual products that are elements of this set, I've changed the elements because I've changed the order of multiplication here. But on a set level, it's the same set because of normality. And now the n prime is beside the n, and that can be absorbed in. As before, the same justification there in the red. Since n prime n equals n as before. I mean, n2 was just some specific element from n. n1 is just another element from n. And then I can swing the b prime back. Because again, since n is normal. Okay, so you've had to use the normality of n twice there. But it comes through. Okay. Okay, the questions about that? Yeah. So now we know the operation is well defined. This definition is perfectly good, or the original definition. Well, that's the same. This definition is perfectly good. It doesn't matter which particular element A you're choosing to represent this, which particular element B you're choosing to represent this. The product of them will always land in the same coset. So to complete my diagram there, I ought to indicate one of these other elements in there as A prime, B prime. That will always be the case. Choose any element from here, multiply by any element from here in the original group G, it'll always land up in the same coset. So that's what it is. And that is because the element is subgroup is normal. Okay, let's briefly look at one of the. Oh yeah, sorry, that's what I'm saying. So now we know the operation is well defined. Then the group axioms check out easily. So the rest of Theorem 10.4, the group axioms check out quite easily. Gn clearly closed under the operation. In the way we set the operation up, if you multiply two cosets, you get another coset. So that's clear. G, the factor group is the set of cosets. Associativity. Associativity follows from associativity on G. Let's just look at that. What associativity means, if you have an AN times a BN times a CN, let's bracket it up one way, like this. So by definition, this is the coset AN times the coset BCN. And by definition, that is the element A times BC times N. But now you can use associativity on G, because this triple product here is an element of G. G is a group, so that operation is associative. So that can be split up A, B, C, N, and then you just break it apart the other way. This is A, B, N, that coset times this coset C, and then so that's the coset A, N, B, N times C, N. See the lovely way in which it folds out. Associativity on this new structure that we've built out of the existing structure of G, it gets its group theory property of associativity from the group theory property of associativity on the original group G. That's the really nice way that it happens. So many times in mathematics like this, you see this kind of thing. The new structure that you've developed, built on old things, it gets its properties from the properties of the things you built it out. It's extremely natural. Or the other group axioms. It's closed, it's associative. It has to be an identity element. Now, it's a coset. So which element goes there? If I held a gun to your head and said, I'm going to hold a gun to Jonathan's head, which is the identity element? Which element goes in front of N? Name one. I'm going to pull the trigger.
Yeah. What? The identity.
Yeah. Which other element could it be? It'd be so perverse if it was some non-identity element that generated the identity element. Sorry for trying to kill you, but just to emphasize the point how natural it is. It is the obvious thing. That is the identity element. Now, you could have answered with what other answer could you give? Maybe not necessarily the identity. Which other elements would generate the same coset? Anything from N. Anything from N. Yeah. So you could have been smart and answered any old element from it. But the identity is the obvious choice. The identity is the obvious. And that's clear because if you multiply it by another coset, by definition it's AEN, but by definition that's AN because A times E is the identity. And inverses. So I'm threatening to kill Mark now. Which element represents the inverse? So I want, okay, Mark's in danger here. I want the inverse of this element.
Oh,
Yeah, has to, yeah, it has to be a coset, so I have to decide which coset it is, which representative it is. But, you know, what else could it be? It has to be the one represented by A inverse. Okay? Everything is so natural in this, okay? And, you know, if you want to prove that, multiply them together. Well, by the definition of multiplication, this is AA inverse times N. AA inverse is the identity. And we've already decided that this coset is the identity element in the factor group. So that's basically the proof of it. That's basically the proof of theorem 10.4. So most of the work, the hard work, the subtle technical work was in proving that the operation is well defined to begin with. And that turns on the normality of the subgroup. Yeah. So another way to look at it is, you know, if you start off with any subgroup and you look at the cosets, the system of cosets, what property do you need to form this natural group out of the set of cosets? If you looked at it that way and you examined it that way, you say, well, I would want to multiply together cosets like this because it's the most natural way to do it. But then you run up against the problem of, well, is it well defined? And so this kind of leads you to why the definition of normality is the way it is. The appropriate condition that tells you this will be well defined when you look at the kind of thing it has to satisfy, you have to have this property that the subgroup is normal. Okay, and I hesitate to say, or I'd venture to almost say that if you took any old subgroup, tried to form the operation like this, but then you worry about the problem of well-definedness, I think it'll only be well-defined if the subgroup is normal. So that's what normality is. Normality is the solution to the well-definedness problem of this natural operation multiplication. I could be slightly wrong in saying that, but that's the kind of main feeling I have about it. Okay, I won't try and jam a lot of other stuff in there at the end.